We now talk about projective space. You start with an affine space, take the 0 out of it, and then you use the equivalence relation, which is represented by this tilde. So what is this tilde? So 2 points are identified if they are scalar multiple of each other. So this is in n plus 1, there are n plus 1 coordinates. So you have included 0 here, that's why you have n plus 1. And this x0 to xn is same as y0 to yn if you can take some lambda out as a constant, and this lambda is not 0. So example is, say we are working in RP2. So RP2 means here you will have 3 points here, n plus 1. So say you start with point 1, 2, 3. Now this is same as the point, say 2, 4, 6, because you have multiplied this by a constant 2. This is also the same as a point 1 by 3, 2 by 3, 1. Again, because you have multiplied this entire thing by 1 by 3. Now this is our preferred representation, because you can fixate on one of the coordinates here and then divide others by this coordinate. So this is a representation of RP2 of a single point. So all 3 of them are a single point. Now let us see some examples to make things more clear. Say P0, this is K1, take 0 out, so 0 you always skip out, and you have the same equivalence relationship as this, you just get a single point. Yeah, so say 2 is same as 3, which is same as 4, which is same as root 2, and so on. Why is that? Because now you can divide throughout by 2. You will get 1, which is same as 3 by 2, which is same as 4 by 2, which is same as root 2 by 2. I just arbitrarily picked up 2. You could have picked up 3 and divided by 3. You could have picked up 4 and divided by 4. Doesn't matter. The fundamental point is that you just have a single point here, 1. So 1 is same as all other points. So you have a 1 point. Now come to P1. Now P1 means that you will work with A2. You have n plus 1 here. So you have 2 points. Skip the 0 out because an plus 1 minus 0, and then you modulo out with the equivalence relationship. So this becomes a is to 1 where x1 is not 0. So we essentially have divided out x1. So we have x0 by x1 and x1 by x1 gives you 1. So that's how you have it. So you divide out by x1. Same as this here. We divided out by the third coordinate. Now either you have this or x1 is 0. So there is decomposition in 2 sets. x1 is not 0 and x1 is 0. Both of them are disjoint. Now this you divide both sides by x0. So you have 0 divided by x0, which will obviously give you 0, and you have 1 here. So this is A1 space because you have this A here. This A is in K, and A could be 0. And then this we write as infinity. The second coordinate we write as infinity. So this is also called hyperplane at infinity. Now let us draw this to see how things look like. So all these lines, this an plus 1 lines, these are passing through point 0. So you have point 0, 0. This is not in your space, but Pn consists of one-dimensional vector spaces which pass through this point. So let us make this more precise. So you have all these lines which pass through it. So all these lines are like this, passing through these points. So each of these lines is just a single point. And to visualize this, and this is 0, 0, 0, which is not in your projective space, but you're talking about all lines which pass through the point 0, 0. And each of these lines is equivalent to just a point. So that is what the equivalence relation is saying. So each of this line is equivalent to a point. So to see this, is what you do is you draw a line here and see where all these lines cut. So all the points on the line correspond to a line passing through the origin. So each point in P1 can be put in one-to-one correspondence with this line, except this line which will not intersect this line here. So this is called the line at infinity. So this is the line at infinity. This is the one here, and this A1 is right here. And that is the story. You can also think of it in terms of stereographic projection, and that is equivalent to this. So we can copy this down here to Pn. So again you will have x0 to xn minus 1 1, so that is this portion here. You have divided everything out by xn. Obviously we are again using the same procedure right here, and because here xn is not 0, in this portion xn is 0, so you have a disjoint union, xn not 0 and xn is 0. Now this is called, space is called Pn minus 1, because you will just consider these 2 points and forget this point which is 0. Now this is called hyperplane at infinity. So this is hyperplane at infinity, and notice that it is given by this equation xn is equal to 0. So this is a closed set. So now when you're talking about Pn minus 1, you have to make sure that all of them do not vanish simultaneously. So point 0 0 0, all of them 0 is not in this set. This is not inside Pn minus 1. That's why we are writing this here. Now you have this an right here, and the rest was Pn minus 1. And then you can repeat the same procedure again, and you will slowly decompose it into affine pieces. So you can have Pn and say it is built up like this of affine pieces. Now you can talk about charts on Pn. So Pn acts like a manifold. You have an open set of Pn, and that you can, this open set you can put in correspondence with the AIN. This I represents this I here, and notice you have an here. So projective space itself is built out of an plus 1, as we have seen here, but its open sets you can put in correspondence with an. So by definition open set is xi, which is not 0. So you take this, so obviously these are n plus 1 points starting from 0, so, or they are in Pn. The ith coordinate is not 0. You divide everything by I, so at the ith position you will have 1. So we skip this one because it's just a constant. So you have skipped 1, but now you have n components here. You started with n plus 1 components, and you ended up with n components, precisely because you skipped this 1 out here. Now you can go from this n coordinates to n plus 1 coordinates, chart in the opposite direction. So you have chart in this direction, now we are going in this direction. So what you're doing is you're just inserting 1 here. You start with n coordinates, you're starting with 0, but then you're skipping I, so you have n coordinates. You go back here, you insert a 1. So you can put open sets in correspondence with this affine chart. Let us see this in a diagrammatic form. How do curves look like when we do this procedure? So say you have curve xy equals to z square. Now you have 3 coordinates, so you will have 3 affine charts. So the first chart is you put z equals to 1. If you put z equals to 1, the curve you get is xy equals to 1. So this is the curve for xy equals to 1. So this is one chart. The second chart you can put y as 1. So this you get as x equals to z square. In the third chart, you obviously put x equals to 1 now, and you get y equals to z square. So this is a projective curve. So it is homogeneous of degree 2, and we have divided into 3 charts, and all 3 charts it looks different.